Hey, how's it going? Let's see. So the talk today is going to be about Looijenga's conjecture and a resolution of it motivated by mirror symmetry. So the goal of the talk is to outline a proof of Looijenga's Cusp conjecture, which I will introduce soon. And this work can be found on the archive 1409.7676. And Looijenga's conjecture was actually proven using methods of mirror symmetry by Gross, Hacking, and Kiel in 2001. And this sort of uses some more combinatorial classical methods to derive the same result. But ultimately, it's also motivated by mirror symmetry. So let's start with a little bit of background. So first, I'm going to define the notion of an anti-canonical pair. Which we'll denote by YD, is a smooth rational surface Y with a reduced nodal anti-canonical divisor D in the anti-canonical linear system of Y. So the picture you should be thinking about for these guys is a chain of smooth rational curves that form a cycle. So by the genus formula, the genus of an anti-canonical divisor on a rational surface has to be 1. And so what this D looks like is going to be a sum of rational curves d1 through dn that form a cycle like this. All right, so yeah, so a smooth, complete, rational, surface, exactly. So let's do a few examples. P2 with the union of a line and a conic that meet transversely at 2 distinct points. And what I'm going to do is I'm going to label each of these curves by their self-intersections. So the self-intersection of a line in P2 is 1. The self-intersection of a conic is 4. Or, for example, we could take the same surface P2, but find a different anti-canonical divisor, like 3 crossing lines. Or if we have the nth Hirzebruch surface, it has an anti-canonical divisor, which is a square, looking like this. And I want to introduce one more definition. A toric pair is a pair YD such that Y is toric and D is the toric boundary. So for example, these two pairs are both toric pairs, but this one is not. Even though P2 is a toric surface, this is not the toric boundary of P2. All right, so a sort of related definition is of a cusp singularity. A cusp singularity is an isolated normal surface singularity algebraic surface singularity whose minimal resolution is a reduced cycle of rational curves. So for example, I could have a cusp singularity P, and its minimal resolution is going to be something that looks like this. And as before, I'm going to label by the... You don't... Yeah, so no trees. You could add trees, of course, by blowing up, but we're taking the minimal resolution. So yeah, there's no, it's just, yeah, just the cycle. So as before, if we label these by self-intersections, we might have something like this. All the self-intersections have to be negative because this arrangement of curves is going to be contractible. Or I'll also draw cases of two components or one component. The one component case is just an irreducible nodal curve. Okay. And the condition that this arrangement of curves is contractible is just the condition that the intersection matrix of these components is negative definite. So that's just Artin's contractibility criterion. So if we write the minimal resolution D as D1 through Dn, then the intersection matrix Di dot Dj has to be negative definite, which is just the statement that Di squared is less than or equal to -2 for all I, and Di squared is less than or equal to -3 for some I. This is if and only if. Note that there are no components of self-intersection -1 because the resolution is minimal. All right, so a remark is that the analytic germ of a cusp singularity is uniquely determined by the self-intersections. Di squared. And that was proven by Laufer in 1974. Essentially, he classified all of the singularities whose analytic germ is uniquely determined by the intersection graph of the minimal resolution labeled with their self-intersections. He called those singularities taut singularities. Oh, yeah, that's true. Yeah, this, if I does not equal 1, or if n does not equal 1. If the length of the cycle is, right, if the length of the cycle is 1, it just needs to be negative. That's right. All right, so you might ask, well, why are we calling them cusp singularities? I haven't really said anything about cusps. So the reason is that there exists a complex non-algebraic Hirzebruch-Jung surface which I'll call V naught, whose only curves are the components of two disjoint contractible cycles. D and D prime, with D plus D prime, an anti-canonical divisor on the surface V naught. And I still haven't said why cusp, which is constructed as a quotient of H cross C, the upper half space cross C, by an arithmetic group. Maybe I should say a compactification of a quotient. And so this H cross C has a certain discrete group acting on it associated to a real quadratic field. You compactify it by adding two cusp singularities, and you can resolve them to get two disjoint cycles. Sorry. So let me just draw a picture of this. So this is my picture of the Hirzebruch-Jung surface. It has two disjoint contractible cycles on it. You could take the contraction, I'll put 2 bars here to indicate that I'm going to contract both cycles to get a surface with two cusp singularities, P and P prime. And this V naught double bar has no curves on it. It has no meromorphic functions. And it's constructed as a quotient of H cross C by this discrete group. So this was done by Inoue. I guess this is Inoue in 1977.
That's after the name was given.
After the name.
Anyway.
Oh yeah. Why is it? Yeah. What did he call them? Oh yeah, that's true. He didn't call them cusp singularities. Yeah. I can't remember what he called them actually. I don't know if he gave them a name. Like the list of taught singularities is like this big list that lots of the singularities I think are not named on them. All right, so let's look a little bit more closely at the Hirzebruch-Jung surface. So, but before I do that, I'm going to make a definition. D and D prime are called dual cycles, and the contractions P and P prime are dual cusps. So in particular, there's a notion of duality of cusp singularities. And the dual of the dual is the original thing, because given any contractible cycle, there's a unique Hirzebruch-Jung surface that contains it, and the other cycle it contains is uniquely determined as the dual cycle. So that's actually a way to define duality of the cusps.
So there are many fields of the
Yeah, for every... Exactly, yeah. So the arithmetic group is inside a real quadratic field. And depending on what real quadratic field that is, you'll get different pairs of dual cusps. So, yeah, so, and furthermore, any cusp singularity appears on some Hirzebruch-Jung surface. So the Hirzebruch-Jung surfaces are in bijective correspondence with pairs of dual cusps. Yeah, so we're going to get to that. There's something very beautiful relating them. So let's ask the main question in all of singularity theory. The main question about any singularity is whether it's smoothable. Well, I don't know if that's actually, I mean, maybe. Maybe that's an overgeneralization. But it's certainly an important question about singularities. So I'm going to mention a theorem that was proven by Looijenga in 1981, which says the following. A smoothing of the cusp singularity P prime can be globalized to a smoothing of the partially contracted Hirzebruch-Jung surface. So I'll just draw a picture of V naught bar, which equals the surface where I've contracted, I think I put D over here, right? D, but I've just contracted P prime. And he did this by looking at the Kodaira-Spencer map associated to the contracted Hirzebruch-Jung surface. But in particular, what we get is a family, I'll call it Y, over delta, an analytic disk, such that the central fiber, Y naught, is the partially contracted Hirzebruch-Jung surface, V naught bar, and the general fiber, well, if we smooth this P prime, so I'll use squigglies to indicate smoothings. Okay, so we smooth it, and so P prime goes away. So we get that. Well, what is that? This general fiber is actually going to be an anti-canonical pair. So and YT is an anti-canonical pair. So, I mean, initially when I saw this, I thought it was kind of counterintuitive. We have a family of smooth rational surfaces, algebraic surfaces, that are degenerating to a surface with no meromorphic functions. But it's totally possible. It's just weird. I'll keep the dual cusps. Are there any questions so far? All right. Let me erase that. Up there. So what are we seeing? Well, we're seeing a sort of surprising relation between a cusp singularity and its dual. In particular, if P prime is smoothable, then there exists an anti-canonical pair, Y, with D as its anti-canonical divisor. Right. Yeah, you may not have a smoothing. Some cusp singularities are not smoothable. So, but if a cusp singularity is smoothable, then the minimal resolution of the dual cusp appears as the anti-canonical divisor on some rational surface, amazingly. And so Looijenga's conjecture is the converse. Which I'll write out just to be totally precise. If there exists an anti-canonical pair YD, then P prime is smoothable. All right, so let's talk a little bit about progress towards the conjecture. So oh, these are. I mean, the central fiber is not algebraic. The central fiber is this Hirzebruch-Jung surface. Oh, this, wait, sorry, what's algebraic? Yes, exactly. YT is an anti-canonical pair. In particular, it's a smooth rational surface, which is always algebraic. Okay, so yeah, that's a good question. So what happens is when you contract pi 1 of the Hirzebruch-Jung surface is Z. It's generated by a loop around the cycle. When you contract it, you get a simply connected surface. But when you smooth it, you get a simply connected surface with an anti-canonical divisor. And by the classification of surfaces, that must be rational. Yeah. Yeah, exactly. So yeah, it's surprising. I mean, I think it's yeah, I guess it's like possible that, well, I mean, I'm not sure. I don't know completely the details, but I think, I mean, you can prove that the general fiber here is simply connected. Yeah. So, okay. So let's. Any other questions? Okay. I know it's like kind of the statements are kind of difficult to wrap your head around. I initially had a lot of trouble. Okay. So let's talk about progress towards the conjecture. So. An approach taken by Friedman and Miranda in 1983 was to resolve the threefold y over delta. And the way to do that, well, you have to make some base changes, but after some base changes, you can produce a family x over delta, which is significantly nicer than our original family. So our original family had the partially contracted Hirzebruch-Jung surface as the central fiber. And so the threefold is actually singular at the point P, the threefold y. And so if you resolve the threefold, and if you know about type 3 degenerations of K3 surfaces, and the theorem of Kulikov, Person, Pinkham, then you can produce a family. So you can produce a family x over delta I guess I should do a dotted line since they're bimeromorphic modifications. We can produce a family x over delta such that the total space is smooth. the central fiber is simple normal crossings. And the anti-canonical bundle of the family has as an element some D, which restricts to D on every fiber. So essentially, what you do is this D is really just coming along for the ride in the smoothing as the anti-canonical divisor. But then at this point P prime, you can resolve it until it satisfies these three conditions. And this statement that the anti-canonical bundle restricts to D on every fiber is saying that the canonical bundle is like trivial near this point P prime. So let's write down some properties that this central fiber x0 satisfies. So it's a simple normal crossings union of surfaces VI, and it satisfies the following conditions. So first, after the very first blow up of this family at P prime, the cycle P prime gets resolved on this surface. And so V0, the first surface in this central fiber, is the Hirzebruch-Jung surface with cycles D and D prime. While all the surfaces VI are rational surfaces. As you might expect, when you blow up, you introduce rational surfaces as exceptional divisors. The next condition is that if Dij is a double curve of x0 joining Vi to Vj, then Dij restricted to Vi, when you take its self-intersection and you add it to the double curve when you restrict it to Vj, and you take that self-intersection, you get -2. So this condition is essentially going to say that near P prime, the canonical bundle is trivial. And the next condition is that if we set Di to be the union of the double curves lying on Vi, then Vi Di is an anti-canonical pair. And finally, the fourth condition, which will actually be the most important one for this talk, is that the dual complex of the central fiber is a triangulation of S2. So just to review what the dual complex is, let's say I have three surfaces in this simple normal crossing surface, in three irreducible components of x0, Vi, Vj, and Vk. I take a point for each surface, and I produce an edge for each double curve. So whenever there's a double curve joining Vi and Vj, I draw an edge. And here's Djk for a double curve joining them. And then finally, whenever I have a triple point, I introduce a triangular face into the dual complex. So that's just a little part of the dual complex. But the whole dual complex of x naught needs to triangulate a sphere. Are there any questions so far? I think it's generally, something like this is generally going to be true if you have like a simple normal crossings central fiber of a threefold with trivial canonical bundle. So long as, yeah, I think that's true. Because, well, I mean, this doesn't have trivial canonical bundle. I mean, it has this D as an anticanonical divisor. But if the canonical bundle were trivial, we would be in the case of a so-called type 3 degeneration of K3 surfaces. Yeah. So that would, I mean, that would necessarily be either a degeneration of abelian surfaces or a degeneration of K3 surfaces. If it's a degeneration of K3 surface, this dual complex is a triangulation of S2. If it's a degeneration of abelian surfaces, it's a triangulation of T2, a two-dimensional torus. All right, so let's introduce a definition. I'll try not to erase this, this thing for the rest of the talk. So if I'm about to, you can yell at me. So definition, a surface x naught satisfying 1 through 4 is a type 3 anticanonical pair x naught D. So it's just like type 3 K3 surfaces, but this time it's like a type 3 degeneration of anticanonical pairs, not K3 surfaces. All right. So amazingly, so Friedman and Morgan in the same paper that I mentioned, or Miranda, I'm sorry, proved in 1983, or proved in this paper that, what did they prove? Any type 3 anticanonical pair, pair x naught D smooths to an anticanonical pair YD. And what does this give us? Well, it gives us something. It actually gives us a criterion for smoothability of a cusp singularity. So let's call x over delta, as usual, the smoothing of x naught. A smoothing of x naught. Then, also in 1983, Shepard-Barron showed that the union of the surfaces from I equals 1 to n of the VI. So in other words, all the exceptional divisors we introduced by blowing up here can be contracted in such a situation for any smoothing of a type 3 anticanonical pair. So this is contractible. Thus, then the contraction, let's call it again, y over delta, is a smoothing of the cusp singularity P prime. So yeah, so it's a surface x, a simple normal crossing surface satisfying these four conditions.
Okay, so this is the reverse of the process that we described.
Exactly. So what Looijenga first considered this smoothing. Friedman and Miranda did two things. First, they resolved this smoothing at the point P prime to produce a central fiber satisfying these conditions. But they conversely showed that a surface satisfying these conditions smooths in a threefold, and that the union of these surfaces can be contracted to produce a smoothing of P prime. And so, yeah, so it's, I mean, it's very nice. I mean, it's a really good result. And in particular, it gives a criterion for smoothability. So I'll do an example soon of a type 3 anticanonical pair. But first, let me mention, what does this show? This shows that the existence of a type 3 anticanonical pair x naught d implies that P prime is smoothable. So you could call this almost Looijenga's conjecture. Because Looijenga's conjecture would just be given by removing the words type 3 here. All right. Let's do an example of one of these simple normal crossings, central fibers.
So there must be a notion of type 2.
Yeah.
Okay.
Yeah, definitely. So the Hirzebruch-Jung surface is also called a hyperbolic Inouye surface. There's something called a parabolic Inouye surface. If you smooth a simple elliptic singularity on a parabolic Inouye surface, you end up getting a smoothing, yeah. You end up getting an anticanonical pair again. But the cycle is not negative definite, it's negative semi-definite. I mean, it's like a boundary case, sort of this case. This is like the widest, this gives like the widest sort of class of examples. So, okay, so let's draw a picture. Okay. So what I'm going to do is I'm going to draw something whose dual complex is a triangulation of the sphere. I'm going to call, so it's going to have three faces corresponding to three irreducible components. So we'll have V naught, V1, and V2. So V naught is going to be the Hirzebruch. Yeah, so that's true. Like, because they showed that you could resolve like this, it's actually if and only if. Yeah, that's right. Okay, so this outer surface, V naught, is going to be the Hirzebruch-Inouye with D prime is equal to minus 6 minus 2, and D is equal to minus 4 minus 2 minus 2 minus 2, which is the dual cycle to this cycle. And then V1 is going to be, well, let me draw some numbers here. I'm going to label this graph 0, 2, V2, minus 4, 4. So V naught is the Hirzebruch-Jung surface with two cycles on it, this one and this one. V1 is going to be a rational surface. So it'll be the blow-up at 3 points of P2 with an anti-canonical divisor, unit of a line and a conic, where I've blown up 1 point on the line and 2 points on the conic. So that produces a rational surface with an anti-canonical divisor whose components have self-intersections 0 and 2. And then, let's see. No, not going to erase that. The surface V2 is also relatively easily realized as an anti-canonical pair. V2 we could realize as the blow-up at 5 points of P2 with the same anti-canonical divisor, in this case in which I've blown up 5 points on the line. 2, 3, 4, 5. And so that produces an anti-canonical pair with cycle of self-intersections -4 and 4. And then this formula about the self-intersections, the sum of the self-intersections being -2, is verified just by explicitly checking 0 plus -2 is 2, 2 plus -4 -2, 4 plus -6 is -2. So that's an example of a type 3 anti-canonical pair. And its existence, the existence of X naught proves that the contraction of -6 -2 is smoothable. So what is the missing step here in Looijenga's conjecture? Well, I may have erased the statement of Looijenga's conjecture, but Looijenga's conjecture says that if there exists an anti-canonical pair YD, then P prime is smoothable. We know that if there exists a type 3 anti-canonical pair X naught D, then P prime is smoothable. So the missing step is that if there exists an anti-canonical pair YD, then there exists a type 3 anti-canonical pair. YD. So the problem is really reduced to combinatorics, because the existence of this surface is actually a purely combinatorial condition. And the existence of D as the anti-canonical divisor on a rational surface is also purely combinatorial. So we just need a combinatorial construction. But it turns out that the combinatorial construction is kind of complicated and hard. So
didn't they do in the case where you have like a small number of cycles?
yeah, so using these type 3 anti-canonical pairs YD, Friedman and Miranda were able to prove that all Cusp singularities where the length of the cycle is 3 or less, that were smoothable, that were conjecturally smoothable, were in fact smoothable. But of course, the cycle length can be arbitrarily long. So, and the number of components of these type 3 anti-canonical pairs grows like very large.
Proving that the existence of YD combinatorial that the singularity is coupled, the one in the district, canonical.
Yeah, so You mean the condition that this is combinatorial? So you can explicitly enumerate all minimal anticanonical pairs. Every anticanonical pair is going to be a blow-up of a minimal one. So that's just it's sort of saying that you can, by a sequence of blow-ups, which correspond to changes of the numbers of self-intersections of the cycle, you eventually get to this D. Yeah, so you can express it. It is a combinatorial condition ultimately, though a very complicated one. All right, so let's make a key observation, which I think is the first thing on the handout. So this observation was essentially made by Gross-Hacking and Kiel in their 2001 paper, though they did it for 2011. Yeah. What did I say? Oh, 2011. Yeah, that's right. Okay. So what's the key observation? Well, I'll do an example. So suppose I have a little piece of a type 3 anticanonical pair. The sum of the self-intersections has to be minus 2 for the two sides. Then what you can do is you can sort of, let's see, maybe I need one more. Okay, lattices are not my, board lattices are not my forte. Okay, so what you can do is you can take the fans of each of these surfaces, let's call them V1, V2, and V3, and the fans somehow glue together in an interesting way. So what is the fan? What is the fan of V1 is P1 cross P1 with its toric boundary. So here's the fan of P1 cross P1 with its toric boundary. So that's V1. Now let's draw the fan of V2, which is a blow-up of the first Hirzebruch surface. So the fan of V2, I'm going to draw starting at this point. And now I'm going to draw the fan of V3. And I notice that for each vector sort of spanning a one-dimensional facet of the fan, I get a corresponding double curve. Let me call it E13, E12, E23. And then for this triple point here, I get a sort of triangular face here. It's a face F1, 2, 3. So the key observation, let me phrase it intuitively first. The fans of toric components, so I have to components of x naught yeah, how to fix it? Let's see. Glue together locally to give the dual complex of x naught. And so what you can imagine is you can sort of think of, so our type 3 anticanonical pair its dual complex is a triangulation of S2. And so we have a bunch of triangles that we're decomposing S2 into. And whenever a vertex of the triangulation, a little vertex vi, when a little vertex vi corresponds to a toric pair vi di, we can sort of impose an integral-affine structure at this point. Integral-affine structure. So there are some bad points in this sphere. The vertices corresponding to non-toric pairs. And away from that, I sort of locally have this picture where the edges coming out of the vertex vi in the triangulation sort of have the structure of the fan of the surface vi. So in particular, what do we get from this observation? Let's see. So let's let gamma of x naught denote the dual complex of x naught, and let A denote the set of vertices in the dual complex such that the associated surface VIDI in the type 3 anticanonical pair is not toric. Then if we take the dual complex and we subtract off these points A, we have an integral-affine structure. Then has an integral-affine structure, i.e., so this is a sphere with just some finite number of punctures on it. And the punctured sphere has a set of charts into R2 whose transition functions are valued in SL2Z times Z2, the integral-affine transformation group.
So, I mean, so you say there are some good vertices and some bad vertices?
Yeah, so
couldn't all the vertices be bad?
yeah, that's right. Like, in fact, I just erased an example where none of the vertices were toric. But yeah, that's absolutely correct. But you can actually repair it. So you can, there's a generalization of a fan. There's an integral-affine generalization of a fan. If I have, let's say I have an anti-canonical pair with 5 components, then I can sort of, I could draw a cone over a pentagon and impose an integral-affine structure on this, like such that it locally kind of looked like a fan. So I won't go into too many details, but yeah, that absolutely is something you need to deal with. All right. All right, so let's see. Okay. Okay, so where does mirror symmetry come in? There should be a mirror symplectic four-manifold. I'll call it Y check omega, which has a Lagrangian torus vibration over the dual complex of the central fiber. So this is essentially something that's predicted in the Gross-Siebert program for mirror symmetry. And we can sort of use it as a rubric to prove the missing step. So we're going to guess that Y check is Y, so that Y is its own mirror. And the result is that we're going to construct a type 3 anti-canonical pair by, in fact, looking in the world of symplectic geometry. Okay, so proof of missing step by example. So recall, we want to show there exists a type 3 anti-canonical pair if there exists an anti-canonical pair, YD. I should say X naught D. All right, so let's see. Let's go back to our previous example, where D prime was the cusp -6, -2. There we had that D was this cycle. Of course, we already knew that D prime was smoothable, but we're going to sort of go through the proof using this example. So first of all, there exists an anti-canonical pair YD. In particular, if I blow up at 10 points P1 cross P1 on an anti-canonical square, the following 10 points, then I will get an anti-canonical pair YD. Because this decreases the self-intersection by 4, and these blow-ups decrease it by 2. So D does appear as the anti-canonical divisor on a rational surface. And we have that YD, so YD blows down to a toric anti-canonical pair, which is just P1 cross P1 with its toric boundary. Now, there's a Lagrangian torus vibration on P1 cross P1 with its toric boundary just given by the moment map. So there's a Lagrangian torus vibration over this rectangle. And blowing up corresponds to a certain set of surgeries in symplectic geometry called Symington surgeries, in which for each blow up, you cut out, for each blow up on a component of P1 cross P1, you cut out a triangle resting on the associated edge. So once you do that, you end up getting, what you end up getting is something that after certain identifications, after certain gluings, is an integral-affine sphere with a certain set of singularities. So by doing these surgeries, we can produce the base of a Lagrangian torus vibration. Which is S2 with an integral-affine structure. And triangulating this S2 gives the dual complex of a type 3 anti-canonical pair. So from this integral-affine sphere, you can actually explicitly construct a type 3 anti-canonical pair, X naught D, whose dual complex is this sphere as an integral-affine manifold. So I think I'm done, right? I'm over already. So yeah, that's the general idea at least. All right. Yeah.